Today, we're covering graph neural networks, a critical capability for any AI practitioner working with relational or structured data. Most engineers encounter GNNs in three contexts: knowledge graphs in enterprises, molecular modeling in biotech, and recommendation systems at scale. The distinction between spectral and spatial approaches will directly affect how you architect solutions and which frameworks you choose. This lesson treats GNNs not as an exotic research topic, but as a necessary tool in the modern machine learning stack for problems where objects and their relationships matter equally. By the end of today, you'll understand when GNNs are the right choice, their fundamental limitations, and how to think about scalability in production environments. Our objectives today are concrete and career relevant. First, you need the mathematical foundation to reason about graphs. How adjacency matrices encode structure, what degree distribution means for learning dynamics, and why spectral versus spatial approaches matter differently in research versus production. Second, we'll move through specific architectures: GCN, GraphSAGE, GAT, not just as names, but as distinct design choices with trade offs. Third, we'll examine message passing, the conceptual core of modern GNNs. Fourth, we'll look at real applications where GNNs are already deployed. Finally, and critically, we'll discuss what limits GNNs today: oversmoothing, scalability bottlenecks, and the interpretability gap. These are the problems your team will actually face. The world is relational. When you work in enterprises or applied AI, most of your data sits somewhere on this spectrum. A knowledge graph in a search engine isn't just a database. It's a structured representation where the connections themselves carry semantic meaning. In chemistry and drug discovery, a molecule's graph structure directly determines its properties. Ignoring that structure means ignoring domain knowledge. Social networks are fundamentally relational. Understanding user influence requires modeling the graph. Even seemingly tabular data, customer purchase history, transaction networks, supply chains, often has latent graph structure. The key insight: many problems where you might default to standard neural networks are actually better solved by respecting and learning from the graph structure. Early AI practitioners often miss this and force unstructured approaches on structured problems. It leads to inefficient models and wasted data. Mathematically, a graph is simple: vertices and edges, but the representation matters enormously for implementation and scalability. An adjacency matrix is dense and quadratic in memory, but it unlocks spectral graph theory and elegant matrix operations. Sparse representations, edge lists, coordinate lists save memory but require different algorithmic approaches. Node features are critical. In real applications, nodes carry information. A person in a social network has demographics. A molecule's atoms have properties. Degree distribution tells you about graph structure. Many real networks are power law, meaning a few highly connected nodes dominate. This affects how algorithms behave. A degree 1 node learns differently than a hub with degree 1000. Understanding these fundamentals isn't academic. They drive performance bottlenecks and architectural decisions in production systems. Spectral methods bring signal processing to graphs. The graph Laplacian encodes structural properties. Its eigendecomposition reveals fundamental frequencies of the graph. Convolving in the spectral domain means filtering these frequencies, like audio processing, but for graph data. This is mathematically elegant and interpretable. You're explicitly controlling what frequencies the network learns. Chebyshev polynomials approximate spectral filters without computing eigendecompositions, making it tractable. In research and theoretical work, spectral methods are powerful because they leverage decades of signal processing theory. However, they have drawbacks. The eigendecomposition is expensive for large graphs, and spectral filters are implicit, harder to interpret in practice. In production, you'll encounter spectral ideas more in research papers than in deployed systems, which tend to favor spatial approaches for scalability. Spatial message passing is the modern workhorse of GNNs. The intuition is local and intuitive. Each node collects information from its neighbors, aggregates it, usually via sum or mean, combines with its own features, and applies a nonlinearity. This local computation is repeated across the graph. The key theoretical insight: aggregation must be permutation invariant. Neighbor 1, 2, 3 in any order should produce the same result. This constraint guides architectural choices. Spatially, you're implicitly computing convolutions. Information from distance k neighbors reaches a node after k layers. The advantage over spectral methods, spatial approaches are embarrassingly parallelizable. A node's update doesn't depend on global eigendecomposition. It depends only on neighbors. This is why PyTorch geometric and DGL favor spatial designs. If you're building GNNs at scale, spatial message passing is your operational paradigm. GCN is the foundational GNN architecture and likely what you'll encounter first. It's elegant. Neighbors contribute equally weighted by their degree, preventing high-degree nodes from dominating. The degree normalization is a design choice with real implications. Because GCNs propagate information quickly, the network can reach all neighbors in just a few layers. This creates a critical practical issue. Layers beyond 3 or 4 often hurt performance. Why? Over-smoothing. After many layers, all node representations converge toward a similar mean, losing discriminative information. This is a fundamental challenge in GNNs and why many production systems stay shallow. GCN remains a baseline. If your problem is node classification on a single graph, GCN is often competitive and interpretable. But it's not universal. Different tasks and graph structures benefit from architectural variance. Understanding GCN deeply, not just the equations, but why those choices exist, teaches you the reasoning behind all GNN design. GraphSAGE introduced a critical practical insight. You don't need all neighbors. Sampling a fixed-size neighborhood makes GNNs tractable on billion-node graphs. This shift unlocked production GNN systems. The inductive framing is important. Instead of learning node-specific parameters, GraphSAGE learns aggregation functions. This means you can generalize to unseen nodes, a requirement in real applications. Multi-hop sampling extends this. You sample k neighbors at each layer, growing receptively but keeping computation bounded. This enables mini-batch training. You can process the graph in chunks, not all at once. The engineering trade-off is real. Sampling introduces variance. A node's representation depends on which neighbors you sampled. This is acceptable and even beneficial with proper implementation, but it means your model is stochastic. In production systems at scale, LinkedIn, Alibaba, Meta, sampling-based approaches dominate. If you're deploying GNNs on real data with millions of nodes, sampling is not optional, it's architectural. GAT brings attention mechanisms to graphs, letting the network learn which neighbors matter for each node. Instead of fixed aggregation weights, attention learns affinities. Neighbor contributions are weighted by a learned attention score. Multi-head attention compounds this. Multiple aggregation heads operate in parallel, each learning different importance patterns. This increases expressivity. The network can adapt its aggregation strategy per node and per head. From a career perspective, attention is now the standard in modern NLP and vision. Applying it to graphs was a natural progression. GATs are more expressive than GCNs and empirically often outperform them on node classification. The interpretability angle is real. Looking at attention weights can reveal which neighbors influenced a node's representation. However, this interpretability shouldn't be overstated. Attention weights correlate with importance but don't guarantee causal explanations. In your work, use GAT when you need expressivity and can afford the computational cost. For constrained systems, simpler aggregation may suffice. Most real-world graphs aren't homogeneous. A knowledge graph has entities and multiple relation types. A social network has users, items, and interactions that vary by context. Heterogeneous GNNs extend the framework. Different edge types have different aggregation functions, reflecting the semantic distinctions in your data. This adds complexity but is necessary for fidelity. Dynamic graphs add time. Nodes and edges appear and disappear. A social network evolves. Transaction graphs are inherently temporal. Temporal GNNs and recurrent architectures handle this. Early AI professionals often build GNNs on clean static toy graphs. Real work is messier. Knowledge graphs at enterprises have hundreds of relation types. Social networks at scale are dynamic and heterogeneous. Building GNNs that handle this complexity is an engineering and design challenge. These architectures, heterogeneous GNNs, temporal layers, are active research areas, which means fewer production patterns and more design freedom, but also more risk. If you're building on dynamic or heterogeneous data, expect less off-the-shelf tooling and more custom engineering. GNNs solve distinct tasks differently. Node classification, predicting properties of nodes, is transductive on a single graph. You're learning on the observed graph and scoring all nodes. This is how GCN was originally framed and is common in recommendation systems and knowledge graphs. Graph classification is different. You have many graphs and want to classify each one. This requires pooling, aggregating node embeddings to a single graph representation. The distinction matters architecturally. Transductive learning doesn't require generalization to new graphs. You can overfit to the single observed graph structure. Graph classification requires learning patterns that generalize across different graphs. Inductive learning, generalizing to unseen nodes in the same graph or entirely new graphs, sits in between. It's the most challenging and most relevant to production systems where you encounter new data. Most real applications combine all three. You might classify nodes and graphs, handle both transductive and inductive settings, and work with evolving data. Understanding which setting applies to your problem guides your architectural choices. Link prediction is a fundamental task. Given node embeddings, predict if an edge exists or should exist. This appears in recommendation systems. Will this user interact with this item? Knowledge graph completion. Should this fact be in the graph? And social networks, friend suggestion. The architecture is simple. Encode nodes with a GNN, then score pairs with a decoder. The decoder can be a dot product, an MLP, or a more complex function. The challenge is data imbalance. Positive edges are rare relative to possible negative edges. Sampling strategies, negative sampling, importance weighting handle this. Graph generation is frontier research, generating graphs that satisfy constraints. Autoregressive approaches generate one node and edge at a time. Variational methods learn latent distributions. This is active research with few production systems. However, link prediction is practical and deployed. If you're building recommendation systems or knowledge graph completion, link prediction with GNNs is a standard approach. Graph generation remains more niche, primarily in molecular design and research. GNNs are already deployed in high-impact applications. In chemistry and drug discovery, molecular GNNs predict whether a compound is toxic or active, accelerating screening and reducing wet lab costs. DeepMind and others use them routinely. In tech, social networks apply GNNs for friend recommendations and influence analysis. Alibaba and Tencent use GNNs on user item interaction graphs for recommendation. Knowledge graphs at Google, Meta, and startups leverage GNNs for search and question answering. These aren't research projects, they're production systems serving billions of users and decisions. Emerging applications are also interesting. Traffic networks for congestion prediction, biological networks for protein function annotation, code graphs for program synthesis. If you're entering AI in the next few years, GNN competency is increasingly a career differentiator. It signals that you can work with structured data and non-Euclidean problems, skills that distinguish you from practitioners limited to unstructured text or images. It signals that you can work with structured data and non-Euclidean problems, skills that distinguish you from practitioners limited to unstructured text or images. GNNs face real challenges that research is actively addressing. Oversmoothing is fundamental. As you stack layers, information mixes and nodes converge. This limits network depth and, consequently, receptive field. Workarounds exist: skip connections, residual networks, implicit layers. But the problem isn't solved. Scalability is engineering heavy. Sampling reduces memory, but sampling variance introduces noise. Distributed training is harder on graphs than on images because communication patterns are irregular. Generalization remains weak. A GNN trained on citation networks may not transfer to social networks or molecules. Graph structure is dataset specific and architectural priors don't always travel. Interpretability is challenging. Attention weights suggest importance, but they're not explanations. Why did the network predict this node is fraudulent? The graph structure and learned weights don't directly answer causal questions. Finally, benchmark bias. Most GNN research uses citation networks and protein interaction graphs, relatively small, well-behaved datasets. Real-world graphs are messier. Power law degree distributions, missing data, shifting edge definitions. If you deploy a GNN and it underperforms benchmarks, this mismatch is often why. Understanding these challenges prevents overstating what GNNs can do. Let's consolidate the core insight. When your data has inherent structure, relationships between entities, GNNs are a powerful framework for learning representations that respect that structure. The mechanics are message passing. Neighbors influence nodes, aggregation pools that influence, nonlinearities introduce expressivity. You now understand the spectrum from spectral elegance to spatial scalability. Spectral methods are theoretically grounded but computationally expensive. Spatial approaches, GCN, GraphSAGE, GAT, are practical. Sampling and inductive learning are what make GNNs work on real-world scales. Research continues on fundamental challenges: oversmoothing, interpretability, generalization. Your career development in GNNs depends on staying current. Read papers from major conferences, ICLR, NeurIPS, ICML, and follow applications in your domain. GNNs are not a one-off topic. They're a growing toolkit for structured reasoning in AI. Tomorrow we dive into representation learning and embeddings, which share principles with GNNs but apply to other domains. This knowledge compounds.